hidden behind the sun, untouchable, unobservable for 2 crucial weeks. That's where 3I/Atlas, the third known interstellar visitor, vanished in late October 2025, just as its chemistry and motion began defying every expectation. Official briefings called it a comet with an alien signature, an unheard-of 8:1 carbon dioxide to water ratio, and stepwise brightening no one could model. All major observatories went dark as it slipped into the solar blind spot, a strategic blackout with a global campaign poised for its return. Something big is going to happen with 3I/Atlas, but is this the hallmark of a cosmic wanderer or evidence of something designed? As the window reopens, the real test is about to begin. The system's automated pipeline flagged its path as hyperbolic, an orbit not bound to the sun, but arriving from deep space and destined to leave again. Hours later, pre-discovery images surfaced from June, confirming the object's trajectory and ruling out a solar system origin. This was only the third time astronomers had caught an interstellar visitor in the act. The designation 3I/Atlas placed it in rare company, following Oumuamua and Borisov, but initial readings hinted at something even more significant. Survey cadence was relentless. Every 24 hours, Atlas swept the southern sky, cross-referencing each new detection with a growing archive. The team, led by Dr. Hanai Myrick, debated the data in real time, aware that a misstep could echo across the field. Early drafts of the discovery memo show a scramble to verify. Was this truly interstellar or just another hyperactive long-period comet? The answer came from the numbers. Velocity clocked at over 58 kilometers per second, outbound on a course straight from the direction of Sagittarius with no gravitational leash to the sun. Size estimates arrived next. The object's nucleus appeared large, possibly the biggest interstellar body ever detected, with a mass in the tens of billions of tons. But it wasn't just the scale that set off alarms. Activity in the coma, the cloud of gas and dust surrounding the nucleus, was already visible at a distance where most comets stay dormant. Each new frame added urgency. Scheduling became a race against time, as observatories worldwide began shifting resources, knowing that the window for detailed study would close fast. For planetary scientists, the stakes stretched beyond a single discovery. Every interstellar visitor offers a rare chance to test what's possible in other star systems. Atlas's catch wasn't just a data point, it was an open door, and the countdown to a global campaign had already begun. Late October brings a blackout that no telescope on Earth can penetrate. As 3I/Atlas sweeps behind the sun, its path lines up almost perfectly with our star, leaving ground observatories effectively blind. Solar elongation drops below 30 degrees, well inside the danger zone for optical sensors, so even the most powerful arrays are forced to stand down. For nearly 3 weeks, every major facility faces a hard stop. The comet is there, but unreachable, hidden in the glare. During this interval, the only eyes with a chance belong to spacecraft scattered across the inner solar system. Mars orbiters, with their unique vantage, keep watch as long as geometry allows. But for Earth, the gap is total. No real-time imaging, no light curves, no fresh spectra. The last usable data trickle in just before October 21st, and then the signal flatlines. This is more than a technical inconvenience. It's a strategic blind spot. The period from late October through early November covers critical milestones. Perihelion on October 29th, when solar heating could trigger outbursts, fragmentation, or even course changes. Any event in this window, explosive brightening, dust jets, a sudden deviation in trajectory, would go unrecorded by Earth's best instruments. Only delayed telemetry from Mars-based assets, with their own cadence and coverage gaps, could fill the void. Anticipation builds as the calendar turns to November. Every observatory schedules rapid response sessions for the moment. 3I/Atlas reappears, with instruments primed to catch the first photons. The operations window, set for November 21st through December 5th, becomes a global watch period. Teams prepare for a flood of data, hoping to catch any sign that the comet's behavior during the blackout was ordinary, or something else entirely. For now, all anyone can do is wait, and speculate about what might be unfolding out of sight. Spectrographs tuned to the coma of 3I/ATLAS report a chemical landscape that defies expectation. The first surprise arrives with the ratio of carbon dioxide to water vapor. Most comets, even those fresh from the Oort cloud, show water as the dominant volatile. Here, carbon dioxide outpaces water by nearly 8-to-1. This isn't a rounding error or a calibration glitch. Multiple instruments, including the James Webb Space Telescope's near-infrared spectrograph and Mars orbiter spectrometers, converge on the same result. The numbers stand more than 6 standard deviations above the trend line for solar system comets. Only one previous outlier, C/2016 R2, comes close, and even that object never showed such a sustained excess. Alongside the carbon dioxide, the coma carries a cargo of complex organics, hydrocarbons and nitrile-bearing molecules, detected at concentrations that startle even the most seasoned planetary chemists. These molecules, rare in typical comets, hint at a formation environment or a processing history that doesn't match anything in the solar system's archives. Some argue for deep interstellar radiation effects. Others point to the possible presence of primordial ices from a distant, carbon-rich disk. Photometric monitoring adds another anomaly. Instead of the expected smooth brightening as the comet nears the Sun, 3I/ATLAS displays step-like jumps in brightness, sudden, switch-like increases that resist easy explanation. Each jump is confirmed across independent datasets, ruling out instrumental error. The light curve's irregularity raises questions about what lies beneath the surface, and whether the activity is driven by patchy jets, buried volatiles, or something less familiar. For now, the data force a pause. The chemistry and photometry refuse to settle into any familiar pattern, leaving the field open for both natural and extraordinary interpretations. Hubble's first clear image of 3I/ATLAS caught the astronomy community off guard. Instead of the jagged, misshapen nucleus common to most comets, the data pointed to a body both large and remarkably smooth, nearly spherical, with a diameter estimated between 2 and 5 kilometers. The surface, at least in the available resolution, showed none of the deep pits or sharp protrusions that mark most solar system visitors. This geometry isn't just an aesthetic detail. A smooth, round nucleus resists standard explanations about how comets form and evolve, especially after eons in deep space. Attention shifted to the dust. Interferometric arrays and Mars orbiter images revealed an asymmetric coma, stretching into a distinct teardrop shape. The dust cloud didn't fan out evenly from the nucleus. Instead, it streamed away in a single, elongated lobe, with hints of layered structure along the sunward axis. Some frames suggested a sharply defined edge, almost as if a boundary separated dense inner jets from the more diffuse outer halo. Models run against these images struggled to reproduce the pattern with typical outgassing or solar wind effects alone. Estimates of the object's mass, tens of billions of tons, made the observed activity even harder to square with standard comet physics. The combination of size, smoothness, and the sharp asymmetry in the coma forced observers to reconsider both the formation history and the possible mechanisms at work. For the upcoming re-emergence, ground-based interferometry and high-cadence imaging campaigns are set to target these structural clues, hoping to catch any rapid changes or new features as 3I/ATLAS swings back into view. October 3, 2025, gave Mars a rare advantage. As 3I/ATLAS swept within 0.19 astronomical units of the red planet, the geometry placed Mars orbiters in a position Earth could only envy. At the European Space Agency, Dr. Amélie Giraud, the imaging campaign lead, pushed for an all-in approach. She argued that Mars Express and the ExoMars Trace Gas Orbiter, TGO, could catch details impossible from Earth, especially with the Sun soon to block the view. Giraud's team executed a sequence of rapid exposures, each just 5 seconds long, tuned to pull faint signals from a background 30,000 times brighter than their usual Martian targets. The gamble paid off. TGO's Cassis camera and Mars Express's high-resolution channel delivered the first close-pass images of the interstellar nucleus, capturing the asymmetric coma and that sharp teardrop dust signature. Spectrometers aboard the orbiters logged data on gas composition, while Omega and SpyCam focused on mapping the distribution of volatiles. The data latency, hours to a day, meant that findings arrived in batches, but they filled a crucial gap. As Earth's telescopes went dark in late October, Mars-based assets kept the story alive, recording every detectable change in brightness, shape, and chemistry. Giraud's decision to risk observation time on an unproven target ensured that when the solar blind spot closed in, planetary scientists still had a window into the unknown. The October 3rd campaign didn't just fill a gap. It set the baseline for everything that would follow when 3I/ATLAS finally re-emerged into Earth's view. Earth's largest telescopes and deep space probes are poised for the return of 3I/ATLAS. The European Southern Observatory's Very Large Telescope, or VLT, has scheduled a series of interferometric runs for early December. By combining the light from multiple 8-meter mirrors, the VLT will resolve structures in the coma and nucleus down to scales of about 100 kilometers, sharp enough to catch changes in dust geometry or surface features that might have shifted during conjunction. Their plan calls for high-cadence imaging and polarimetry, targeting the asymmetric tail and searching for evidence of new jets or fragments. Meanwhile, the JUICE spacecraft, on its way to Jupiter, will attempt a rare compositional study as 3I/ATLAS sweeps through the outer solar system. JUICE's suite of ultraviolet and infrared spectrometers is tuned for faint, fast-moving targets. With its unique vantage, the probe can sample the comet's spectrum in a different geometry from Earth, helping to confirm or challenge the anomalous carbon dioxide and organic signatures reported earlier. The timing is tight. JUICE's window for observation only opens after perihelion, as the comet heads outbound. On the ground, global networks like the VLT and Gemini are coordinating to monitor light curves, rotation, and any signs of non-gravitational acceleration. The goal is simple: catch every deviation, no matter how small, and build a complete record as 3I/ATLAS re-enters view. With more than a dozen instruments in play, the coming weeks promise the most detailed post-conjunction scrutiny ever applied to an interstellar visitor. Every new observation of 3I/ATLAS sharpens the divide between natural and engineered explanations. On one side, planetary scientists point to the volatile physics at play. The carbon dioxide-dominated coma, with its 8-to-1 ratio over water vapor, could signal a nucleus formed near the carbon dioxide ice line in a distant protoplanetary disk. Some suggest cosmic ray exposure during its interstellar journey may have altered the surface, creating a crust that traps water beneath and leaves more volatile ices exposed. The asymmetric teardrop dust geometry and step-like brightness jumps might then reflect uneven outgassing, localized jets breaking through a patchy, radiation-processed shell. The repeating 17.3-hour rotation pattern, while unusual, fits models where irregular outbursts torque the nucleus into a slow tumble. Yet, the engineered scenario refuses to fade. Skeptics within the spectroscopic community, like Dr. Elena Varga, point to the timing and symmetry. The smooth, nearly spherical nucleus is rare among comets, where most show battered, irregular forms. The object's arrival, threading a path between Mars and Jupiter, with perihelion hidden in the solar blind spot, strikes some as deliberate. The step-like brightening, if it repeats with precision, could hint at a controlled energy release rather than chaotic venting. For Varga, the most telling test lies in the details. Does the light curve reveal on-off transitions, or is it just stochastic activity from exotic ices? Is the coma's sharp boundary a product of natural jets or a sign of engineered containment? Both camps agree on one point: extraordinary claims demand extraordinary evidence. Each hypothesis now stands as a set of predictions. If 3I/ATLAS fades in line with volatile-driven models and its path remains consistent with known outgassing physics, the case for a natural origin strengthens. If, instead, the post-conjunction data show sustained non-gravitational shifts, stable periodicity in brightness surges, or spectral lines that defy known chemistry, the debate will escalate. The next round of data will not just inform, it will decide. Every prediction for 3I/Atlas now comes down to a handful of measurable signs. The first is the light curve. If the comet's brightness fades smoothly after perihelion, settling from magnitude 10 to 14 in the weeks after conjunction, it argues for a natural, volatile-driven process. Any major deviation, like repeatable stepwise jumps in brightness or sudden surges at fixed intervals, pushes the case for something stranger. Photometry teams are watching for these switch-like transitions, comparing real-time magnitude readings against a baseline model built from pre-conjunction data. Rotation is the second anchor. The 17.3-hour periodicity, seen in the object's modulated light, should remain stable if outgassing is random or naturally chaotic. A sudden shift in the spin rate, or a pattern that repeats with machine-like regularity, would raise new questions. Observers are logging the phase of each brightness peak, looking for signs of artificial modulation or abrupt changes in the rotation axis. Trajectory is the third test. Astrometric tracking, measuring the comet's position against background stars, can reveal non-gravitational accelerations. For most comets, these are subtle, caused by uneven jets of gas and dust. For 3I/Atlas, any sustained deviation beyond a few centimeters per second squared, or a course correction not explained by standard outgassing models, would stand out in the residuals. Teams are using predictions from July through November as their reference, flagging any shift that exceeds the noise floor set by Mars and Earth-based observations. Spectral evolution rounds out the checklist. If the carbon dioxide to water ratio and complex organics fade as the comet recedes from the Sun, it would match expectations for exposed, volatile-rich ices. But if these features persist or new, unexplained lines appear in the infrared or radio bands, the anomaly deepens. Every instrument, from ground-based arrays to JUICE and JWST, is tuned for these transitions. The final tool is the viewer's own watch list. Track the predicted magnitude band, note any sudden shifts in tail or jet direction. Watch for stability in the 17.3-hour rotation, and compare the published trajectory with the model, especially any post-conjunction course corrections. Extraordinary claims demand extraordinary evidence, but every data point in the coming weeks will tip the scale one way or another. As of now, whether these anomalies reflect exotic natural chemistry or something engineered remains unresolved. Key questions, such as the source of the stepwise brightening and the precise cause of the asymmetric dust, await post-conjunction data. What is clear, every major observatory is watching, and the evidence gathered between November 21st and December 5th will decide if 3I/Atlas rewrites the story of interstellar visitors or simply expands the boundaries of what is possible in nature.